Hi, I'm Sammy, and today we'll be going over KeySweeper. KeySweeper is a stealthy Arduino-based device camouflaged as a functioning USB wall charger that wirelessly sniffs, decrypts, logs, and reports back all keystrokes from any Microsoft wireless keyboard in the vicinity. The keystrokes are stored online and locally within the device. SMS alerts are sent to you if any trigger words, URLs, passwords, etc. are typed by the user. A web-based interface is supported to show you what the user is typing on the keyboard at all times live. And if unplugged, KeySweeper continues to operate using an internal battery that automatically recharges as soon as it's plugged back into the wall. So first, I'll do a little demonstration, and then I'll show you how to build your own KeySweeper device, how the entire thing works, and how to protect against it. So here you can see me logging into my Linux laptop using a Microsoft wireless keyboard, and immediately the keystrokes are sent over the internet back to a web interface. So first let's go over the hardware within the KeySweeper device. The first thing I'm using is a microcontroller. Here you can use something like a Teensy that we used in USB drive-by, or in this case I'm specifically using a Arduino Pro Mini. Specifically a 3.3 volt version. They also have a 5 volt version. I like this because it's only a few dollars on eBay for a clone, and also if you're running at 3.3 volts, that means you can also operate it with a 3.7 volt lithium polymer battery. Now, most of the time this whole device will be plugged into the wall using a USB charger, so technically the USB charger inside will be powering it. But by adding an internal battery, what we can do is when the user unplugs this from the wall, this can continue to run in the background using the battery. As soon as the user plugs this back into the wall, it then it actually moves over to the wall power or AC power, and then will charge this battery back up. The next thing that's critical for this is this device. This is called an NRF24L01 Plus. It's a Nordic radio frequency chip that communicates on 2.4 gigahertz. It uses kind of its own proprietary protocol for communication. You can't really talk to Wi-Fi or Bluetooth. Technically, there are a few packets you can get here and there on some of those protocols, but that's not the intent of the chip. Now, this is pretty much mandatory to sniff keystrokes on the Microsoft wireless keyboards because they are using a proprietary 2.4 gigahertz protocol. They're not using Bluetooth, they're not using Wi-Fi, and we'll go into how to actually determine that in the next part here. Of course, we are also using a USB charger. Now, originally, this is a charger I got off of Adafruit. I like it because it has this screw, so you can actually unscrew this and open it up and then take everything out. What I did was I actually took an iPhone charger or an iPhone charger clone, and I took the charger out of that, which normally looks like this square right here. And I took it out and I found that it actually opens up. There's just a little flap here. And because this is much smaller than the charger in here, I then swapped out the hardware in the bigger charger, put in the smaller one, and now I can fit all sorts of other parts in here. So here I have an open version. I can stick this charger in here. I can then easily stuff the Arduino in here. You can put the NRF24L01 Plus. Also, these NRF chips come with some pins soldered on. I just solder those off for this device because this take too much room. And the last piece of this device is this. This is an Adafruit phono board. This allows us to use a SIM card, which does GSM. So we can then send us SMSs, receive SMSs. It can use the internet over 2G. So this is actually live broadcasting any keystrokes over the internet so that I can live monitor the user or users. It can also actually send and receive calls. So we can actually stuff that in there as well, and all the devices will fit inside of this with a battery as well. If you wanted to go an inexpensive route, the phono board is about $40, $45. If you wanted to get rid of that, you could actually just use a charger. In fact, you don't even need a charger if you just want to power it via battery or USB. And really all you need is Arduino or Teensy and the NRF chip. The NRF chip is $1 on eBay. That's after shipping. The Arduino you can get for about $3 for a clone, so just a few dollars. Additionally, you can add an SPI chip or a flash chip. What this allows you to do is just add a lot more storage onto the Arduino. So if you wanted to log locally onto your key sweeper device, you could actually have all the keystrokes just stored on here. That way you can come back another time with either a wireless device that then sweeps all the keystrokes from this device wirelessly, or you can just pull this device from the wall, walk away, and pull everything off the SPI chip later. Now, when I first got this keyboard a few weeks ago, I had no idea what protocol it actually communicated in. I knew it was wireless, but I didn't know what frequency it was talking on. So the first thing we need to do is figure out what frequency it is communicating on, because I do want to sniff these keystrokes without just using the USB dongle if I wanted to create a device like KeySweeper. So in the US and many other countries, there's usually a regulatory body that controls radio communication. So if you want to, say, sell a device that transmits on a certain frequency, you actually have to register. And in the US, we have something called the FCC. And the FCC requires that all these manufacturers actually put an FCC identifier on the back of their devices. So here we can actually see an identifier. On this, it says C3K1455. And the FCC's website actually lets us search that. So once we pull that up, we can now see the frequency range that this wireless keyboard transmits on. And according to the FCC website, that's 2403 megahertz through 2480 megahertz. So immediately we know this is on 2.4 gigahertz, equivalent to 2400 megahertz. So there are a couple other protocols on 2.4 gigahertz. There's Wi-Fi, there's Bluetooth, Bluetooth Low Energy, Zigbee, a couple others. However, the fact that it also came with its own USB dongle means to me that it's probably using something proprietary. If it were using Bluetooth, we would just be able to pair it with Bluetooth and wouldn't need this. So if it's proprietary, I have a couple of guesses of what chips it could be using inside, but we won't really know without opening it up. So the next thing I did was I opened this keyboard up, and you'll see that it has only one chip or one integrated circuit that's controlling pretty much everything on board here. And now if we look closer to that, we can see that it says on that chip something like NRF24LE1H, which sounds a lot like a chip I'm familiar with called the NRF24L01 Plus, but it is different. Now, if we take a look at what this NRF, if we Google NRF24LE1H, we find a website from Nordic, and what this chip is a system on a chip. So it actually contains both a CPU or microcontroller and a radio chip. The radio chip happens to be one that I'm familiar with called the NRF24L01 Plus. Now, that's what's going to be interesting to us. That means that this little chip on the keyboard is not only controlling the processor, but it's also controlling the radio communication. Now, normally if I were trying to sniff something like this, if the radio chip and the CPU or MCU were separate, I would be able to use a logic analyzer and sniff in between the lines that are connecting the microcontroller and the radio chip. But because this is integrated, I can't actually do that. I can't use the logic analyzer to help in this scenario. So instead, we'll actually have to sniff 2.4 gigahertz packets to see what this is communicating. The good thing is, because it's using a radio that we know and we can look up the datasheet, we can see kind of how it's communicating. So the next thing is to start sniffing packets to see what is going across this chip. Now, to sniff 2.4 gigahertz packets, there's a couple things we can do. We can use something like HackRF1 from Michael Osman. This is an amazing device. It can do transmit, receive, all the way up to around 6 gigahertz. Incredible for its price. We could also use something like an RTL SDR, which we've used in a previous video. Unfortunately, the RTL SDR typically is limited to around 1.7 or 2.2 gigahertz, so it's just shy of the 2.4 gigahertz that we're sniffing here. However, there's something called a down converter that we can get that's maybe another $20 that allows higher frequency signals to get down converted to something that the RTL SDR can sniff. Now, ultimately, we don't want to use something like RTL SDR or HackRF1 because we want something very small. We want an embedded device that we can, let's say, leave in an office that's just constantly sniffing and doesn't have a big RTL SDR antenna or a big, HackRF1 board. So doing a little research on the NRF24L01 Plus chip, the radio chip, I found a great website from Travis Goodspeed. Travis Goodspeed is the author of GoodFET, a hardware device that makes it really easy to interact or interface with different pieces of hardware, and a number of other pieces of hardware and software. And Travis actually did some research a while ago on similar Microsoft keyboards, and he used an NRF24L01 chip, the same radio chip that we're using, to sniff 2.4 gigahertz packets. What's really interesting about Travis's work is that he found that these chips don't actually support sniffing. These chips only provide communication, receive and transmit. But to do that, you need to specify who you're communicating with. You need to specify a MAC address between 3 and 5 bytes that says, okay, we're communicating with this person. The problem is we have no idea what MAC address the keyboard is on, or the USB dongle is on. But with some clever tricks and testing, Travis was able to actually sniff using this $1 radio chip on the 2.4 gigahertz frequency, which is awesome. So we use his work to start sniffing. When the NRF chip typically sends a packet, it will send the packet in this format. We'll have a 1 byte preamble, which tells the radio that a packet is about to come. We'll have a 3 to 5 byte MAC address, which tells which radio that this packet is for. We'll have an optional packet control field, which contains options to tell the radio to behave a certain way. Then we'll have the payload. The payload is the only data we actually ever see. The radio will cut off everything. It'll cut off the preamble. It'll cut off the MAC address, which is pretty important to us because we need to know the MAC address of the keyboard to sniff it. Additionally, all of these packets will have a CRC or a checksum. And if for any reason the radio detects that the CRC or checksum doesn't match the rest of the packet, it'll drop it. Now, Travis found that if we set the MAC address to the preamble, we can actually confuse the radio. And the radio will sometimes see a preamble come in and think it's the MAC address. Now, once it does that, it thinks everything after the preamble, everything after the MAC address is the payload, so it now sends us the payload. But the payload now includes the MAC address of the keyboard. We can see this in a drawing that Travis did here. So Travis found not only by setting the preamble or setting the MAC address to the preamble, but he also found an invalid option that you can set these MAC addresses. Since normally it's 3 to 5 bytes, he found a way that you can actually set it down to 2 bytes. It's technically invalid. Now you might also say, well, the checksum or CRC won't match because it's now an invalid packet, but you can simply disable CRCs within the radio and it will send you the packet no matter what. So using this awesome discovery from Travis, we can now sniff keyboard packets. Now, in my testing, I used Travis's GoodFET device with the NRF chip and a host computer. This is an awesome combination because in Python, we can write code to basically talk to this radio, and it makes it very fast and great for rapid prototyping and testing. Travis has already included a program called goodfet.nrf, which allows us to read from the NRF chip and even sniff keystrokes from a keyboard like this, which is awesome. Now, in our implementation, we can't really have a laptop. We can't bring a laptop with Python on it or a GoodFET, connected to a GoodFET. So instead, I've ported a lot of that code to C so that we can load it onto a teensy microcontroller or an Arduino. Another thing that I've done is I've found that if we look at the FCC, we found that we're only using the frequencies 2403 to 2480. So that's about 78 megahertz to look at. Normally the 2.4 gigahertz band is about 128 megahertz. So we can actually reduce our scan from 128 megahertz down to 78, which greatly increases the speed of scanning for these keyboards. Another thing I found from all of these different keyboards, from Travis's research and also research from a project called KeyCarry, which I'll go into later, is that all of the MAC addresses of these keyboards start with the hex characters CD, or 0xCD. Now, this is great for us because if we know that the first byte always is a 0xC or a hex C, which starts with a 1 bit, we know which preamble the radio will use. The radio will actually use a different preamble depending on the first bit, whether the bit is a 1 or a 0, because the preamble is alternating bits. So it will either be 1010 or 0101, and that preamble is decided upon by the first bit of the MAC address. So now we don't have to choose the two different preambles, 0x55 or 0xAA. we always know it's going to be 0xAA because of the MAC address. So this also cuts our scan in 50% again. So we're actually reduce the scan even further. So now when we're scanning for a keyboard, we can do it even faster. Another thing I found from all of these keyboards is that normally the NRF chip allows you to communicate in 2 megabits per second and 1 megabit per second. But I found that all Microsoft keyboards are always communicating at 2 megabits per second. So again, we cut it in half. Now our scan time is much, much lower. Additionally, I found that because all packets within the keyboard are have a fixed header of some sort, it's either going to be a type of key press packet or an idle packet. And these two types of packets have fixed headers that are entirely unencrypted. If we look for those, and we look for the 0xCD as the first byte of the MAC address, we will always know when we see a keyboard packet. So instead of sort of sitting around waiting for a number of these packets to come through, we only need to see one packet, and then we know instantly that this is in fact a Microsoft keyboard. So this actually brings down our scan from traditionally from 85 minutes to about a minute. So it takes less than a minute to scan for a keyboard, and once it's found the channel that keyboard is on, it sticks there, it programs it into the Arduino. Our code will program that frequency into the Arduino so that it will always know to look at that channel and instantly begin sniffing that keyboard. So now that we have a small, portable, and fast device that's capable of scanning and sniffing Microsoft wireless keyboards, the next thing we need to do is decrypt the traffic or decrypt the keystrokes that the keyboard is sending. So we find that there's a project out there called KeyCarry. It was presented by Thorsten Schroeder and Max Moser a few years ago, and it's an awesome project. They found that using these Microsoft wireless keyboards, they fully reverse engineered the protocol and created a device called KeyCarry. It uses two radios and a high-end microcontroller to do the sniffing and perform the decryption. And they found that the encryption process is virtually non-existent. Essentially what they're doing is they're taking the MAC address of the device, which we can determine thanks to Travis's work, and basically performs a bitwise XOR or exclusive OR on each byte. In essentially every 5 bytes, it'll use a 5-byte MAC address and XOR each byte. Now, the problem with this is that the password or the encrypted MAC address never changes. So the password is always the same. And because we can sniff that, we can always decrypt every single byte. Now, after doing some further research, I found that we learned something earlier in that every Microsoft keyboard starts with 0xCD. The CD is the first byte of the MAC address in hex. If we actually take a look at the packet, here's a page from the KeyCarry presentation where they show the decryption process of a keystroke. It's this HID code 05, which is the letter B in HID, and CD is the first byte of the MAC address. So you can see that when we XOR C8, which is the encrypted packet, with CD, we get 05. We know that 05 happens to be the letter B. The problem is that it's always going to land on this byte. The HID code, or the keystroke the user's pressing, is always on this specific fixed byte. Now, we already know that every Microsoft keyboard has CD, so we don't even need to know the MAC address anymore to decrypt these packets. All we have to do is always XOR by CD, because we always know that's the first byte of the packet. This allows us to actually decrypt any Microsoft wireless keyboard without even knowing the MAC address anymore, which is great. So just by doing this, we can decrypt the entire packet, and we now know the keystrokes. So this is awesome. So using now a few dollar Arduino and an NRF chip, a $1 Nordic RF chip, we can decrypt these packets and see every keystroke of any keyboard in the vicinity that's using the Microsoft Wireless Keyboard Protocol. It doesn't matter what operating system you're on. I did a demonstration earlier while doing this on Linux. I've tested on Mac and Windows as well. It's entirely unrelated to the operating system of the host computer. Now that we have a device that scans for keyboards, sniffs the keystrokes, and decrypts it all, we actually want to retrieve that in some way. So the next part is the ability to capture those keystrokes remotely. So I provide two methods for this. One is by using the Adafruit Phonoboard. This is an awesome board. You put in a SIM card, and it can do a couple things. It can send and receive SMS text messages, it can make and receive phone calls, and it can use the internet over 2G. So I do a few things if you're using this board. First, I have it send all keystrokes live to a backend server that you control. Using this server, you can actually hit a web page using some PHP and jQuery that I've created that allows you to live monitor the user typing on the keyboard. So as soon as they're typing keystrokes, you're seeing it live over the internet. Another thing this does is that I've programmed it to send you SMSs upon certain trigger words. For example, let's say you knew at some point they're going to log into Twitter. They're going to go to twitter.com at some point. So whenever they type twitter.com, you could set that as a trigger. Once they type twitter.com, it measures or it sniffs another 20-30 keystrokes, and then it sends that to you, and it sends it over SMS. So you don't have to constantly monitor keystrokes that they're typing. You simply get an alert on your phone that says twitter.com, username, password. Now, it doesn't matter that Twitter is using HTTPS or SSL or TLS encryption, because all of this is happening before the keystrokes ever hit the computer, right? This is just happening within the radio frequency from the keyboard to the USB dongle connected to their computer. And because it's entirely passive, they have no idea that you're sniffing. So this is one way of doing it. I also support a more inexpensive method. So let's say you didn't want to use this board, or you wanted to create a much smaller version of this device. You could limit it to just the Arduino and just the NRF chip together. Now, the NRF chip has a cool feature where it can actually monitor or listen for packets from multiple channels or multiple MAC addresses. So while we have one, they're called RX pipes or receive pipes. While we have one receive pipe listening to the Microsoft keyboard, we actually have a second receive pipe open. And that second receive pipe is looking for a specific MAC address that I've pre-programmed. So you can actually create a secondary device that I call the back tracer. And essentially, if you ever walk near this USB charger or the key sweeper device with a secondary device, they will detect each other. And this one, the one plugged into the wall that's sniffing all the keystrokes, will send all the keystrokes it's logged back to your device. Both of these can be powered either by battery or by the wall charger. So you never actually have to go and pick up the device again. You never have to touch the key sweeper device. That can just be plugged into a wall forever. The last piece of the key sweeper device is where we embed it. And I decided to actually embed it inside of a USB wall charger to basically hide it in plain sight. Now, if you see a USB wall charger and it's plugged in, you just don't really think about it. The fact that it's plugged in most times, or that you can leave it in a wall pretty covertly, means that it can constantly be powered. So we can always run off of power and not worry about someone unplugging it. The cool thing is, if someone does decide to unplug this, because all of our devices are so low power, I also include a 3.7 volt lithium polymer battery inside. So as soon as it gets unplugged, it switches over from AC to the internal lithium battery. As soon as you plug this back into the wall, it then moves back from the battery to AC power and simultaneously recharges the internal battery. So at no point do you ever lose any keystrokes that you are sniffing wirelessly. So the way I decided to do this was I found a USB charger. This is a 1 amp or 1000 milliamp USB charger from Adafruit. I like this one because it has a screw, so we can actually unscrew to open it. I find a lot of USB chargers are actually very difficult to open. They're either glued or connected together in other ways that to open them you typically have to destroy them, where this you can just unscrew. Now, because inside of here there's a rectifier that converts AC power to DC power, and then that DC power goes from the high voltage that AC mains power is at down to 5 volts, which USB uses 5 volts. This takes up most of the space. So what I ended up doing was, while we use this bigger device, I found a smaller iPhone charger and opened it up. When we open it up, we see that inside this sort of square actually opens up into this thinner device. Now, this thinner device easily fits into here with a bunch of space for our battery, Arduino, NRF chip, and even our GSM board. So once we stuff all of that in there, then we want to power it all. Now, I specifically chose a 3.3 volt Arduino device for a few reasons. For one, it's just lower power. It's better than a 5 volt device if we can do the same amount of work. So we're using less power. Another thing is that if we want to use a 3.7 volt lithium battery, we can't power a 5 volt Arduino or any 5 volt device with a 3.7 volt device. So we use a 3.7 volt device or battery to power the 3.3 volt Arduino. The Arduino itself has a voltage regulator, so you can give it anywhere from 3.35 to 12 volts, and it will regulate it down to a smooth 3.3 volts. This is great because the other chip that we're using, the NRF, also requires a lower voltage. We can't give it 5 volts. We can't even give it 3.7 volts. It maxes out at around 3.6 volts according to the data sheet. So we don't ever want to give it more than that or we might fry it. So by using a lower power device, we can use a lithium battery without any additional hardware. Ultimately, we also want the USB charger to work. So I actually leave almost everything wired the same, and I simply pull the 5 volts off of the USB into the Arduino, specifically the raw and ground pins. That will hit the voltage regulator, bring it down to 3.3 volts, and that will power the Arduino as well as the NRF chip. And we also use the 5 volts to power the GSM board. What's interesting about the GSM board is that it has not only voltage regulator, but it also is able to recharge the lithium polymer battery that we have embedded inside, which is great. So whenever it's plugged in, it's constantly keeping that battery charged. One other thing that I did for fun, just on my device, was this USB charger has an LED. So whenever it's plugged in, you see that LED is on. Now, this obviously hurts the covert nature of the device, but for mine, I actually tied the LED to the Arduino instead of to the USB power. Now I have the Arduino power that LED so that it's always on, just like when you plug this in, the light will turn on. However, whenever a user is typing keystrokes, it will then turn the light off for just a moment. So if you actually look at this while users are typing, all of their keystrokes are essentially blinking to this device. It's pretty fun to watch. You might not want to implement that depending on your implementation of this device. And that's the entire KeySweeper device. I've included schematic and a lot of details in a write-up, a bunch of pictures, full source code, and everything else you'll need, including the web-based back end. If you enjoyed this, please hit subscribe and check out some of my other videos. All right, thanks. Bye.